Hi there. Now, here we have a question on connected particles. I'll read through the question, but at any point you might decide you want to pause the video. When you come back, I'll give you the numerical solutions then to parts A and B, and after that, I'll take you through the work solution. So what we've got here then is two particles, A and B. They have masses of 2m and 3m respectively, and the particles are attached to the ends of a light inextensible string. And particle A is held at rest on a smooth horizontal table. The string passes over a smooth pulley which is fixed at the edge of the table. And particle B hangs vertically below the pulley with the string taut as shown. And particle A is released from rest, and assuming that A has not reached the pulley, find in part A the acceleration of B and in part B the tension in the string. And it's 5 marks for the first part, 1 mark for part B. So if you'd like to have a go at this then, and haven't paused the video, just give you a moment to do that. As I say, when you come back, I'll give you the numerical answer and then we'll run through the work solution. Okay, welcome back then if you had a go. So as for the numerical answers, we've got for part A, in terms of g, the acceleration due to gravity, it would be 3/5 g meters per second. And if you take g to be 9.8, it turns out to be 5.88 meters per second. And for part B, the exact answer is 6 mg over 5 newtons. And again, if you take g to be 9.8, it comes out at 11.76 newtons. Or rounding it, say, to 3 sigma figures, it's 11.8 newtons to 3 SF. So, if you would like to see the work solutions, though, I'll take you through those now. So the first thing I'd want to do is just mark on the forces acting on our particles. So we'll start with particle B. We've got its weight acting downwards, so the weight would be its mass, 3m, multiplied by acceleration due to gravity, g, and so that'd be 3 mg newtons. There'll also be a tension acting upwards, which I'll call T newtons. Now if we turn our attention now to particle A, the forces acting on this would be its weight downwards. This would be its mass, 2m, and then multiplied by g, be measured in newtons. There'll be a normal contact force from the surface that we'll call r newtons. There'll also be a tension in the string, wanting to pull it to the right here. And that tension is in fact exactly the same as the tension we've got here. It's worth pointing out, by the way, that quite often you're asked, why are the tensions the same in the string? And that's because it's passing over a smooth pulley. Okay, smooth pulley here. Now these will be all the forces acting on A. It's a smooth table, so there will be no friction. If there were, it would be acting towards the left. So they're the forces then. We need to mark on the fact that particle B is accelerating downwards, so we'll just mark that in there as A, so that's A meters per second. And that means that the particle A will also accelerate to the right, and its acceleration will be the same as the acceleration of B. So I'll mark that in as A meters per second. And we're often asked, by the way, again, why are the accelerations the same? So this is just a reminder, if you do get asked that, it's because the string here is inextensible. It doesn't stretch. So as soon as this particle moves, A will move at the same time. Okay, so that's the typical kind of diagram that I would draw for this then. So when it comes to finding accelerations and tensions in problems like this, what we do is we look at each particle separately and we consider Newton's law of motion. That is essentially force equals mass times acceleration. And We do it for each particle and we get simultaneous equations which we should be able to solve for t and a. So let's start then with part A and consider particle A. So we'll just put this down here, consider particle A. And if we do that, we're going to look at resolving our forces, taking positive sense to the right, which is the best thing to do, really. That is, take it in the direction of motion. And so we're looking at the resultant force acting on A in this direction, and we've got all of T acting in that direction. As for R and the weight, these are perpendicular to the direction we're resolving in, so there's no effect. So this is the resultant force, and it's equal to the mass times the acceleration. So the mass is 2m and the acceleration is a. So there's our first equation then. We need to get another equation, and we get this by looking at B. So we're just going to put up here, consider particle B. So consider B. And for this one, what we'll do is we'll resolve downwards in the direction of motion. Okay, so resolving downwards, taking downwards as positive. So the resultant force on B will be the weight, 3mg, so we therefore have got 3mg, and then minus the tension, okay, because that's acting in the opposite sense to this. And this will be equal to the mass times the acceleration. The mass is 3m and the acceleration is a. And we'll call this equation 2. So we've got our two equations now, and we just need to solve them simultaneously. And what I could do here is just simply add my two equations. I could even substitute 2ma into here. It's up to you. I'm just going to add the two equations though. So put that down here, 1 plus 2, to help whoever's reading it. And if we do that, we've got 3mg then. And I see that minus t plus t, that cancels out. And so we're left with it equaling 2ma plus 3ma, which is 5ma. And the m's are in each term, so I could divide both sides by m, and that means that now if I divide by 5 to both sides, I get that therefore the acceleration a is equal to 3g over 5, 3/5 g. And if I take the value of g to be 9.8, then we could get a decimal version for that acceleration. So if I do that, I'll just put here or a equals, well, 3 times 9.8 divided by 5, you'll find that you get 5.88, and that'll be measured meters per second per second. Okay, well, there's the acceleration then, and now we've got to get the tension in the string for 1 mark. So for part B then, it's just a question of substituting our value for acceleration, either this value or this value, say, into one of our equations, 1 or 2. Well, it makes sense to put it into equation 1 because it's a lot simpler. So I'm going to say, call this one here 3. Okay, we'll put that value of A into our equation 1. So just say here, sub equation 3 then into equation 1. And if we do that, we therefore have got the tension T, I might as well write tension here, tension T equals the 2m here multiplied by A, and that will be 3g over 5. And that gives us a total then of 6 mg over 5, and that'd be measured in newtons. And you could leave it like that, it's up to you, or you could take g to be 9.8, and if you do that, it'll be 11.76 m newtons. Or if you round this up, say to 3 significant figures, it'll be 11.8 m newtons to 3 significant figures. As long as you make your methods clear, I'm sure that would be sufficient. Okay.